The final ascent of magma towards the surface of the Earth is strongly influenced by its physical properties that are determined by the chemical composition. Very important factors are the viscosity of the cylindrical liquid and volatile content. Volatiles are all elements that want to escape from magma when pressure is lowered and magma is moving towards the surface of the Earth. Water is particularly important as it is the most abundant volatile. Carbon dioxide is also an important volatile, but there are other volatiles such as sulfur, chlorine, and fluorine. When volatiles are released from fluid magma, they form a free gas phase, resulting in gas bubbles in the magma. This can cause a large change in the physical properties of the magma. This figure from Helge Gunnemann displays schematically a variety of eruption styles and the role of volatile exsolution and expansion. A large part of volcanic gas released in eruptions is water vapor. It is far above the boiling point, as its temperature is the same as the temperature of the magma. The volume of gas is very strongly dependent on pressure. As pressure is released when magma approaches the surface, the gas volume expands, typically by more than 2 orders of magnitude. The volume of the gas phase thus multiplies in volume, and the magma becomes like a foam. The process is similar as to what happens when a bottle of champagne is opened. In that case, it's actually carbon dioxide that is released and causes the foaming. This figure from Gunnemann demonstrates the role of exsolution of volcanic gas from magma in an eruption conduit during the final ascent of magma, and how that relates to different eruption styles. As water is exhaled from the magma, its viscosity increases, and thereby its resistance to expansion. The magma can fragment. Magma fragmentation is the breakup of a continuous volume of molten rock into discrete pieces, sometimes called pyroclasts. Because magma contains bubble of compressible magmatic volatiles, decompression of low viscosity magma leads to rapid expansion. If the magma is highly viscous, resistance to bubble growth will instead lead to excess gas pressure, and the magma will fracture like a glassy solid, resulting in the formation of violently expanding mixture of gas and pyroclasts. Another type of magma fragmentation occurs if magma comes into contact with external ice and water, for example during eruptions that happen on ice-covered volcanoes, when huge volumes of ice can melt. Thermal energy of the magma will vaporize water and quench magma, causing fragmentation. Let's look at each of the panels in this figure separately. This panel A shows a fusive eruption of silicic magma of high viscosity with low ascent rate, where permeable gas flow takes place. A dome-forming eruption occurs. This panel B shows sustained explosive eruption with fragmentation due to gas overpressure. Some degree of magma-water interaction may also occur, but the amount of external water is low. Upon fragmentation, the flow changes from being a melt with suspended bubbles to a mixture of gas with suspended pyroclasts. This panel C shows a phreatomagmatic explosive activity predominantly due to hydromagmatic fragmentation at high water-to-melt ratios. Eruptions of this type can also happen under ice cover, where there is abundance of water due to ice melt. This panel D shows the situation in what is called strombolian type of activity, where large bubble accumulations, called gas slugs, rise through a slowly ascending magma of low viscosity. Finally, panel E shows magma breakup during what is called Hawaiian-style eruption, characterized by high ascent rates and sustained jets composed of gas and pyroclasts. So, the understanding of how volcanic gas escapes from magma and the role of gas bubbles in magma, understanding the viscosity of magma and contribution of external water is a key to understand the behavior of volcanic eruptions.